So, welcome back, everyone. So, last time we were forced to delve a bit into measure theory to understand the continuous histogram. Yeah, this time we hopefully won't need so much measure theory, but can actually think about some applications of the histogram. So, for instance, we will cover histogram equalization, so which is meant to like redistribute the gray values so that you make better use of all the contrast that you can have, and histogram matching, where you can transfer histograms from one image to another. For instance, if you have images of the same object but taken with different sensors, then such a matching is a possibility to like equalize different sensor outputs. Okay, just to very briefly recap. So we had this continuous histogram, which was going from all these Borel sets and assigning them a value, and it was just checking like how often does a certain range of gray values appear. Yeah, so it was a problem if we only count individual gray values, but with this we are like counting ranges of gray values by not only considering a single gray value, but like a certain set of gray values. And with this we had the cumulative distribution function, which also in the continuous case is just a function, and it was just counting the volume or measuring the volume of the sublevel set. And if we just briefly recall how these looked, the red one was the histogram, and of course in the continuous setting, it's you have to visualize it differently because it's a measure. But if you think about it as a density, it would look like this, and the green one also looks like this in the continuous setting, since it is a function. And yeah, just applying it on a different image, you can see there's a quite different distribution of gray values, but nevertheless, you can notice that values that appear often in the image are peaks in the histogram. Yeah, so, but that we should all already know from the last time. And last time we stopped with the concept of binning. Yeah, so if you want to compute a histogram, you sometimes do not want to take like really all the possible gray values and count them individually, but group them into chunks, into bins, yeah, to have like a coarser representation of the histogram, in particular if your image has a high value range like 16 or 32 bits, because then individual values only would appear very, very seldomly. And so let me just briefly recap what we needed for this binning. So we need to set the number of bins, that's M, and the boundaries of the bins, which are just sending the sorted values and making this picture again. Here we have some function f, which you can think of as a continuous image. You can also think of a pixelated image. Yeah, and then we put the different r's here. Here's rm, here's r0, and for every of these intervals, we count, we check where f takes this value. For instance, if we look at this part here, f only takes values in this range in the interval sketched down here. Yeah, so these value ranges, yeah, it's just always between two consecutive boundaries that you have chosen, right open intervals. If you are with your index, if it's not the largest index, and only the very last interval, you take the closed interval. Yeah. So for all of these, the lower boundary belongs to the interval, and the upper does not. That belongs to the next higher one, and the only exemption is the topmost, where you include the boundary. And then the corresponding histogram for bin number k is just the volume of the set where f takes values in this bin. Yeah, and unless you have a specific reason to not uniformly distribute them, you would just uniformly distribute them, starting with the lowest possible value, which is the infimum of our image. And we are then going towards the supremum of the image in evenly distributed chunks. Yeah, so the width here is always 1 over m minus 1, yeah, of each of those times this difference, times this value range. And k is just an index to count, so that we go up here. Yeah, only exception is the last one. There you can, for instance, take supremum plus 1. Yeah, it's really just a boundary problem that when you chop this up into little pieces, you need to decide which boundary goes where. And just a very simple example, so we can check that it's really just counting, and even if we apply it to discrete images, because here this was like a continuous picture, but works all the same in the case of discrete images. So this is my image, and I need to specify what kind of grid this is. It's a Cartesian grid with grid size 1. Now that's this way I know how big this omega is that we are discretizing. And let's take some bins. So m we take as 4. Lowest value of f is obviously 1, highest is 7, so maximum minus minimum is 6. And we're starting at 1. So like this is now 6, m is 4, so we are dividing 6 by 3. That means the intervals have length 2. So the first bin is just 1 to 3. The second one is 3 to 5. The third one is 5 to 7. And the last one is 7 to 8. Yeah, and here in this case, we're just counting now. So for H1, we have to check where does f take values in B1. So bigger equal to 1, smaller than 3. So only values 1 and 2 count for this. And we have 1, 2, 3, 4, 5, 6, 7. So that is just 7. Same here. Here we're just counting the 3s and 4s. 4, yeah, and it's 4. Now we are counting the 4s and 6. We don't have any. And the last one is counting the 7s and 8s, but 8s we cannot have because the maximum is 7. So there's just 1. Yeah? So we have to do something, and this is one way to do it. So you could take this, then the last bin is bigger than every other bin by 1. Yeah. So this is smaller. It's just one choice. Both is possible. Yeah. So this is not just that you have to take this separation. It's just one of the possibilities. Perhaps this could be more natural. Yeah. Okay. So now let's actually do something with the histogram. And this is the equalization that I announced in the beginning. Yeah, so let's go back to one of our images. So the only thing that the normalization that we had earlier will do is it will put the lowest value to 0 and the highest value to 1 or 255, so to black and to white. So that means that the histogram will have a full width after you do the normalization, but this just like spreads things vertically. It does not redistribute values. So this has a lot of dark values and a lot of bright gray values, but very few, very little in between. And the idea of the equalization is that we want to flatten the distribution so that all the gray values are more or less taken equally. Yeah? Yes. So I plan to show you after, but yeah, we can have a look at before we do it actually. Yeah, let's have a look what it does before I tell you how it does this. Yeah, so this is just the normalization I was talking about. We take the lowest value to 0. That's why we get this grayish background to black. And everything is spread, but the peaks stay exactly the same. And here is now what the equalization does. Okay, the first thing that you may notice, it looks probably unnatural. But you can see much more detail in this equalized image than you could see in the original image. So even though it doesn't look very nice, it allows you to see more of the details in there. And what you can see now is that after the equalization, this cumulative distribution function is actually just linear. Yeah? No, it's like trying to shift every single of these gray values to make the cumulative distribution function. So it's not a constant shift. So it's a nonlinear change in intensity. So it really has to redistribute intensities, but it only takes one intensity and assigns it to a different value. So some things will get darker, some things will get brighter, and everything can happen in between. And for this linear cumulative distribution function, you also actually should get in the continuous setting like a flat histogram. Yeah, because it should be evenly distributed. The problem is that in the discrete setting, this doesn't work because you have to send one gray value to one other gray value, so you cannot like split these peaks. Yeah, so if you have 100 pixels with the value 10, you can change the value to 8, but you cannot put half of the pixels with value 10 to value 8, the other half to 9. So that's why this still looks very jaggy in the histogram, but the distribution function, this has the nice slope of 1. I think we have another image here. So here probably looks a bit more natural. So yes. No, which kind of encoding? The precision. No, the problem stays the same. If a certain number of pixels has a specific gray value, no matter if I have 8 or 16-bit or more to represent this, then I cannot assign this one gray value to different gray values. Yeah, so yeah, probably we see this when I show you how to compute it. You can see where it fails. Yeah. Yeah, exactly. So you would have to pick, from an algorithmic position, you would have to make arbitrary decisions like a random reassignment of the value 4. Yeah. Yeah, so it's almost, of course, it is a step function, and so it's no, it's a no, so it's just can we? Yeah, no, it is technically not linear. It is getting as close to a linear slope as possible, but it will just consist of steps. Yeah, so can I see if I can zoom in here? If we really zoom in, yeah, you can see the steps. Yeah, yeah. It's not exactly linear. You just try to get as close to linear CDF as possible. Yeah, yeah. If this redistribution is merging, then you cannot go back. Yeah, that's correct. Yeah, only not merging. You can go back. But usually merging some. Okay. So now in our motivation, why what we're doing. Now we want to figure out how to do this. Yeah, we want to write down all the text that I have in the notes. Just the idea is we want to distribute these gray values as neatly as possible, or uniformly the value change. Yeah, and so I'm trying to assume the value 0, 1, very dedicated to any value, as long as the range is finite, no problem. So and here actually also the continuous use point is very helpful because here you can lose it under certain conditions and then just discretize our continuous solution and get an idea that does the job also for discrete images. So and first we need to exactly specify what we are looking for. So we want to reduce our identities so that we have a linear CDF and this means in particular we look for a bijective increasing intensity transformation T that defines our given values to other values. And of course, we need to combine this with this condition on the CDF. So we want that the CDF of the intensity transformed image. So if we take our original F and we apply our intensity transformation, we want to be S times the volume of omega. Yeah, so we wanted to increase linearly and the slope is just volume because we know that if we plug in 1 here, since f has value smaller to 1, the value for s equal to 1 has volume of the entire domain. Yeah, because it just captures the entire domain. Okay, yeah. Yeah, for the discrete image, we just will discretize the solution. No, it's not bijective merging. Or splitting or so in this case, after discretizing, we will merging, but also this is an assumption. So we try to find the solution in an idealized case where this bijectivity is possible. Yeah, so it's like you start with a very restricted case where you find the exact solution, and then you transfer the solution of this simplified case to more general cases where you use some guarantees, but still preserve the properties that you will look for, like in that properties manner. Yeah, but this will have many mathematical formulations, and you need to make some assumptions, and not always all these assumptions will be fulfilled for data that you actually use. Okay, so this is what we would like to have. Now we have to figure out how to choose this T, because that's the only thing that we can choose to make this happen. And first, why is it still on this? now look at the derivative. The derivative is just the volume. Yeah. We revise back to S, so this is just the one. So the derivative is constant. That means this is an even uniform distribution. Yeah, so this is just to confirm that this is a good thing to look for. And the idea to get that representation of this T is to assume that, let's say we have this already, and see how it looks. Yeah, so let's say we have T that fills this. Then T of S times the volume of S omega. Yeah, we now use that this is a result. So this is G of the transformed image evaluated at position T of S. Yeah, so I just made use of this for S equals T of S. And yeah, so by definition of the PDF, this is just a volume where the transformed image is smaller than T of S. Now we make use of the assumption that T is bijective and increasing. Because since T is bijective and increasing, I can just cancel the T on both sides of the condition. Yeah, so if at some point this it also will without T, and vice versa. So this is the same as volume where F is equal to S. And this is GF of S, just by definition. Yeah, this gives us an idea how the T looks like, because we have T of S here, and we can divide by volume and see what it should look like. And the question is how do we get bijectivity and increasing? So this will need to make some assumptions on this G of T. Yeah, so we now know how it should look like, and some assumptions. This is S such that GLM itself is a continuous mapping from 0, 1, 1 to 0, 0 volume of omega. Yeah, so this continuity is something that we get to assume. So for pixelated images, it is certainly not true. Yeah, the DF has jumped, but for continuous images without jumps, this can be fulfilled. Also, we want the GF is strictly increasing. Strictly increasing. And G of 0 is 0. Yeah, then we found a solution. Then T that goes from 0, 0, 1 to 0, 1, 1, and that is then S to GL of S divided by the volume of omega. This has all our desired properties. And we'll check that now. Yeah. First we can see that we now have a representation of this CDF we actually can compute. Because given an image, we can simply compute this CDF by integrating or counting all these values. And now let's check that we have the properties that we want. So the continuity and strict monotonicity of this GF combined with GF of 0 equals 0. Give us the invertibility of GF on its image. So on GF of 0, 1. But GF of 0, 1, 1 is the entire zero volume of omega. Yeah, so we already know that GF of 1, 1 is volume omega with the extra assumption GF of 0 equals to 0, that's 0, 0 here. Yeah, and something that is continuous and strictly increasing is always invertible. Yeah, so that's how the assumptions go together to give us invertibility. And so now that we know that G is invertible, we can use it to compute the inverse of G to use the invertibility here. So the inverse of S is just GF inverse of S times volume of omega. Yeah, by solving that here. And so first we just assumed that our T fulfills the condition we are looking for. Now we are confirming that we found really fulfills the condition. Because that we don't know yet. Yeah, we just know if it would fulfill it looks like this, but the other way around needs to be checked. So this is the volume of T of F smaller equal S. Just the definition of the computed function. And now we can apply the inverse of T. So this doesn't change the set. So this is F smaller equal T inverse of S. Yeah. We just bring over the T to the other side by applying the inverse of T. And this is the F of the inverse of S. So it's just the definition of GF. Yeah. So this GF by definition is the volume of F smaller equal this argument there. And now we can insert what we know about the inverse. So we have here the inverse, GF the inverse. So it's GF of GF inverse. This cancels, so we just left with S times volume omega. Yeah, and so means we have found the solution of our histogram stabilization based on these assumptions. Yeah. So this requires some property knowledge. And if we have those, we can guarantee to have a linearly increasing CDF. If those are not fulfilled, we will only get an approximately linear CDF, which has these kind of steps we looked at. But how do we do that? Because we now know how can we compute these intensity transformations for a discrete image to get the features that I showed earlier. I should briefly say what the problem is. So if V is discrete, we cannot expect a uniform distributed histogram. And as mentioned earlier, the problem is in one way you can only map exactly one way. Yeah, so you cannot split. But we can still apply the idea. And for this, we take now a pixelated image. Pixelated image with value range of 0 to n, and as usual, capital F, the corresponding discrete image. And now we see rounding mapping. So when I denote this rounding mapping by RD, and what it does, the real number is just mapped with its nearest integer, and if there are two nearest integers exactly at 0.55, you are rounding up. So that means that x is mapped to floor x if x minus floor x is smaller than 1/2, and otherwise we are mapping to floor x plus 1. Yeah, and for the sake of completeness, also define what floor is. That's just the maximum integer. That is smaller or equal to our x. Yeah, so this is that's the floor function, and then the rounding thing. Yes, everything is not negative. It doesn't differ much from the rounding that you may know. But in general, when you're rounding, some rounding functions are rounding towards 0, so that the behavior is different whether you're bigger or smaller than 0. So this one is always rounding up, whether it's positive or negative. That's the main difference. And with this we can now write down approximation of our transformation function for the histogram visualization. So discrete histogram function. So, and we start exactly like our theory suggests. We make the CDF divided by the volume. That is exactly what we found here as the formula for our T. Now we make two small adjustments. So this T was the value range 1, 1. But now our value from follow to n discrete. So we rescale this 0, 1 to n. And then yeah, we have round to great values that we are allowed to use, because we only allow values are 0 to n. So we are just rounding here in nearest integer. So this is like the pixelated image viewpoint. Let's go with this one. But you can also take the discrete image viewpoint where you apply the rounding to n divided by the number of pixels times the probability distribution function of the discrete image. Yeah, if you remember, this is the same effect for scaling pixel volume, and that's why the scale favors here. And this is now something you can just go ahead and apply to your image. And this is exactly what I did to generate those plots. Yeah, so you're computing the CDF, and then you get this transformation function by rounding the scaled CDF to integers and just resembling that. And that's what you get. Yeah, so it's pretty easy to do. You just have the idea that it can be done this way. Okay, so this is the case that you want to equalize the histogram, make good use of your great value range at the price. Possibly the images don't look so natural, but you see a lot of detail. And another application of exactly the same idea is the one of histogram matching. Yeah, and the setting that you can think of is we have images of the same scene taken with different sensors. So, and those can have very different histograms. And the idea of matching is that these histogram differences can be compensated. Now the histograms can be used to compensate these differences. Also with some assumptions. So you cannot compensate by contrast reversal. So if there's no strictly increasing relation between these sensors, you have no chance to be compensated. So keep that in mind. So now let's consider again two images. Again, images. Now we have images. And for being able to apply this histogram equalization from before, we need to assume that these CDFs are invertible. And we take these intensity transformations from the equation. So the one for f is called t, like before, and the one for g now called capital S. I should try to distinguish this as more from the small s. And now he's allowed to transform histogram of one image to the other image. Transfer. The histogram of one image to the other, and yeah, perhaps somebody can guess how I can use these two transformations to make f have a histogram of G, or to have a relative distribution function of G. Keeping in mind that this takes f and makes it uniformly distributed. This takes G and makes G uniformly distributed. So we have to set like in the middle. But from the middle, we just want to wave from one histogram to the other. Does anybody have an idea what we could do? Sorry. Exactly. So we take the one that brings f to uniform distribution. Yeah, so this f should now be uniformly distributed, and since f takes g to the uniform distribution, the inverse of s should take the uniform distribution to the distribution of g. So we just apply s inverse here, and now we check that this actually does what we hope that it does. Yeah, so first we insert the definition of the common distribution function, then we apply the inverse or apply s to get rid of the inverse. So we just have p of f here, and now have capital S of small s on the other side. Now same shape we used before. So we're just moving things from one side of the equation to the other, or equivalent population, and so this is now the CDF of G of S at the position capital S of S. And yeah, we know that G of F is uniformly distributed, so this is just capital S of S times the volume of omega. And by definition of the capital S, this is the CDF of G. And we just plug this. So that means after applying these two transformations, the histogram or the CDF F coincides with the same thing of G. So we can just transform. So the histogram of S inverse G F and G. They coincide. And you can make this even slightly more general. So we did not use that GG is CDF of an image. Just by adjectivity. from 0, 1 to 0 volume of G. So that means we can transfer any arbitrary objective into increasing distribution to N. If for whatever reason you want your histogram to have a certain shape, you can do it with the second approach. So that is one example of what you can do with histogram to get some simple transformation of your image. And now another example of what you can use these concept for is segmentation. Segmentation by stress threshold. Yeah, so we have this T theta, which was mapping where you either 0 or 1. Yeah, if you're below theta 0, above or equal to theta, it was 1. So you would, for instance, convert an image into like a black image with where the two different values and meanings. And as a motivating example, let me show you one example. So this is just a picture of a blackboard, and here to improve the visibility or also to use less data to store it, you would like to find the threshold theta so that the writing is bigger than the theta and the rest smaller, so you have this segmentation. Yeah, and for that, the question is, how can we find theta? Because we don't want to try many of all possible thresholds. And this is what the next example is concerned with. So let's say F is an image of different text. And here we, as I said, we want to reduce the number of variables to 2. Yeah, like text and no text. Which we call segmentation of image. Yeah, and this, for instance, compensates differences in illumination and also reduces the noise, as you can see from the example. And of course, the amount of data is you need to store is reduced significantly because you only need to remember one bit per pixel and then not at least the full byte. So this can be done, as I said, this is the theta threshold. But relies on the proper theta. Yeah, and to illustrate this, I'd like to start with the picture. And if we think about this image of this handwritten text, there will be a lot of background, and there will be a lot of writing. So the histogram will have different peaks. So the background sound has a much higher peak, And if I think now about my chalk on Blackboard, so the background is to remain like this, and then there is some peak of the right here, like background, and this is like right. If we think about writing in front of dark background, of course, what would be the opposite if you just take nominal paper, of course, dark writing on white background, but doesn't have so. And Caesar now means choosing a value here, value range where to make the cut. And so if you look at this histogram, I hope most of you will have an idea where you want to put the cut. Yeah, where you want to put the cut. Yeah, so you would hope to put the Caesar here in the center. So now, sorry. Yes. So this is supposed to be like in the middle between Windig and like, yeah. But the problem is you don't have to fix. Yeah. So of course you could look at the histogram and compute this, or you can try to do some. Yeah. Exactly. Finding the is very difficult, and that's why we will not try. We will not try to find things. So we will have this idea in mind and try to find something that describes the situation without needing to check where things are, but by using a different way to look at the condition. Yeah. But we can compute that. So the CDF then would have like a large slope there where these things are happening. Yeah, so you could look for this, but this would be like a different way to finding the case, but you would need to try to find anything with that idea here. And so what we are doing here is slightly different motivation by the structure, and let me try to explain how that works, or like driving a condition that this here would fulfill. So this thresholding partitions our image into two components. Let's call one sigma. This is where f is smaller equal, and you can think of approximating background processes. And the other component is the complement, which is f bigger or equal to 0, so that's the rest. And the idea is now, so in words, choose theta in such a way that it corresponds to the average of the average gray values in these two areas. So let me write the formula down, then we can check how this relates to the picture. So choose theta such that it corresponds to the average of the average gray values in the two components. Yeah, so what does that mean? Average of the averages. So that means theta is supposed to be 1/2 integral of f over the one component plus average integral of f bigger than theta. Define what this integral means. So this is just the average integral that we are integrating as usual. But we're just dividing by the volume to get the average value of f in that area. Yeah, and so if theta is in that position, then the average gray value of n in here would be roughly the position of the peak, and it would even work like 2 peaks. It would just be sitting inside these peaks. And here, in the simulation, the average intensity of the f in the area where that amplitude gray value is roughly that peak. Yeah, and so the condition is that we fit in the middle of it. Yeah, so that is one way to look at this phrase picture as an equation. So unfortunately, this is a rather complicated equation because the thing that we are looking for here is the integration domain. So now you have to figure out a way how to compute this theta. So we now know what we want to fulfill, but then we need a way to compute it. And so like I read for theta, this is not an option. But just let's call this function of phi, because this is something depends on theta, and we call this phi of theta. And then one thing that one technical detail I still need to mention for this, of course, you can't really take an average value with the area 0. Yeah, so in that case, it doesn't make sense to normalize them. So we need to specify this separately. So if the volume of smaller theta is 0, or the volume of bigger theta is 0, we just consider this is theta. And also the other one. Yeah, this average integral is really not defined for an energy integration domain, and in that case, we just use by definition theta, that we are on the safe side. So while you're doing this, is not happen unless you choose theta completely wrongly. These things will not be applied. Okay, so yeah. Yeah, so the idea is that we want one component because the natural we have writing and background, and we are now trying to figure out what is the best way to find what the components are. So we don't want to really compute everything, but we now want to model what is happening and how can we make use of when we know what's happening and want to compute this threshold. I'm not sure if that answers that question. So feel free to rephrase or so you mean why 2 or why not 3 or 4 segments or yeah, so you can run segmentation with more segments. Yeah, so there are cases where you have more different objects. For instance, you could look in the example for the wall, for the blackboard, or for the writing on the whiteboard. That would be for 3 components. for we started with the task abstract, just to like who is the simplest situation where you can consider simulation. So now with this formulation, our task is find theta such that theta equals phi of theta. Who knows how such an equation is called? Yeah, this is a fixed point equation. And what is the simplest idea that you can have solved a fixed point equation? Point equation. Sorry. So one tool to show the existence of these points. But if you now just want to compute it, if you want exactly. So whenever you see a midpoint iteration, the first thing you can think of, let's just iterate and hope that it will converge. Of course, we would show that, yeah, but this is why you no, that's the idea. So even if you are doing research in America, you want to experiment with new schemes, you first try to do an experiment, and if you see that your idea converges, you try to figure out why is that. But this is the first thing that you might find on this. Usually, I don't know many people who just I don't know many people who would just write down an algorithm and try to prove convergence before actually gathering some with the Americans that it would converge, that there is a chance. But no, of course, America we would. No, this here with 2 has nothing to do with like 2 seconds. So this is just so this pi. So here we don't see anymore that they are 2 seconds. It's just a function that we apply over and over again. So it could oscillate like between. So worst case is just y 4 6. So any kind of can happen in a fixed point scheme unless you have some properties of the function that you are applying. No. So the game cluster could lie to the point in the histogram. The intent value you apply a game cluster with saying that you want 2 clusters, you will get probably roughly these values. But you will have to explicitly say you want 2. If you give it more clusters, it will return more clusters in this case. For sure. But I'm not sure that this answers this question. Okay. So in any case, the idea is to think about integration. So the decay mean will not be a sigma in any case. Which sigma mean in we don't do anything. No. And we also do the cluster. So it's no, the decay mean gives you like roughly clusters, and that's something that encodes the deviation, roughly the clusters and some deviation. So in any case, now let's do this fixed point iteration. Fixed point iteration. So theta n plus 1 equals I theta n for n. And with some initial value. That you have time to choose. No. Typically, in this case, it would just take 1/2 between the infimum and the supremum. So you would not take the mean value usually because the background is way overrepresented in this case. That's why you take the mean of the range. And so this is now called isolated algorithm. The starting value is relevant when some really is right. So if you have a really good nonsense starting value outside the main then that's a problem actually. Then the starting value is nonsense. One of these domains may be empty. Actually, so we will show that for sure. What happens when you start with the boundary area? It's an interesting question. I never thought about nonsense. But something one can think of. So the Banach theorem would be one way to prove existence of the fixed point. Yes, having a factor here is but what we will use instead is we will show convergence by showing monotonicity of our function. So if we can show though that this function itself is monotonic, and we make sure that it takes down 0, 1, then we have monotonic convergence that is bounded, so it has to converge. And actually one needs some more assumptions that the convergence to the fixed point. Because if this phi is very, very bad, the limit could be not be fixed point. But in any case, the convergence is that, and let me show you how this is done. So we know that the range of f is 0, 1, that's our assumption. So we have that also I map 0, 1 to 0, 1. Yeah, because you average 0, 1, of course you get something back in 0, 1. So let's phi is the 0, 1 to itself. So we can apply this, and we know that we never have 0, 1. And now for the monotonicity, let's take two thresholds, 1 and 2, and see what phi does to them. So I start with theta 2, and I write phi a here instead of phi, because I'm only looking at the left half of phi. Yeah, so we have two components. This one and that one, and I just treat this one, show that this is monotonic, and the exactly the same idea can be used to apply it on this one. Because that's the same structure. So now let's do it for the left one, because otherwise the computation also gets quite lengthy both at the same time. So what we want to do is we want to replace this theta 2 with theta 1, and show that the value only gets smaller. And then for this, I need to get this theta 1 where. And the first thing that I do is I write down on what the average integral means. So this line here is just a scaling vector, and the remainder is integral. but I put theta 1 here. So I'm splitting the integration domain further in theta 1 smaller f smaller equal to 2. Yeah, so it's just splitting this larger domain into two smaller domains, and it introduces the theta 1 that I want to have there. In the second I just want like the every integral here and get rid of everything else, and by doing so only get the one smaller. So this is now bigger equal. Now we make it a little bit shorter. So this here is bigger than theta 1 times the volume of the integration domain. Yeah, so I'm integrating a function that is as easy as its value theta 1. So the function I can estimate below theta 1 and just multiply with the volume we are integrating. So this is the lower bound. So we go equal. So I can change that, then get rid of that part, and go on further estimate from below. Yeah, I also just keep this. And I'm also keeping that factor here. No. And I'm estimating the theta 1 low. Oh no, try to finish. So this is now smaller than 1. Yeah, so the integral of f, no, the average integral. So the average integral of f, where f is smaller equal to theta 1 is definitely smaller equal to theta 1. That's how I get this in here. And now we just check all these factors. So this is the same as 1 over this part. I'm adding now the factor f not equal to 1. Theta 1 smaller f smaller theta 2 times this average integral. Yeah, so what I'm doing, so I'm like adding this factor here and also dividing by it. That's why I get this and the mean integral just factoring this out. And the volume of this plus volume of this is exactly the same volume of that because the union of the domain is 1. And so that means this cancels that factor, and what I have left is phi a of the 1. That means phi a is increasing. Yeah, and the other part also increasing. We get the convergence, but since we are out of time, I will finish that during the next lecture next Tuesday. And thank you for your attention.